Hello, everybody. I want to make this little announcement first, and I think this is very important about what will happen next week. What will happen today, this week, and then next week. So how about plan for that will be April the 4th. Okay. Here's the thing. Today I will finish up 5.1, which I left over last time, right? And I will do 5.2 and 5.3. Basically, finished material for test 2. Okay, now next week, on April the 4th, according to class schedule, we're supposed not to have a class, no class. Okay, supposed to be not having class. So, but I will make myself available. But I will go over, but I will go on Zoom and work on previous test 2. The purpose is so that you have something to study during the spring break, if you want to study. Okay, now the week after that, April the 11th, that's a spring break. Okay, I myself do not want to hold a class. Okay, this spring break. Okay, now the thing is, when you come back on April the, let me make sure that's the correct date. No, that's April the 2nd, not the 4th. My bad. My bad. That's April the 2nd. So this will be the 9th when we have spring break. And then the 16th when we come back, that's already test 2. Okay, that's why I hope you understand why I insist to go on Zoom and work on previous test 2, because when you come back, you have test 2 right away, and we never have a chance to go over any old test 2. Okay, now, but what happened is for next week, I will not have attendance. I mean, I may have a sign-in sheet on the discussion board, but I will not hold it against anybody, you know. Okay, because it's supposed to be a no class, and I plan to go over only 2 previous tests. Okay, let me do the sign-in sheet first. Give me a second. I go back to the discussion board. Today we will finish 5.1b, 5.1, and 5.2, 5.3. Okay, next week supposed to be no class day, but I will go on Zoom to go over previous test tools. Okay, and as usual, I don't require attendance anyway, right? But at least I will make the recording available if you want to study during the spring break. You see what I mean? Okay, and here's the thing. Here's the thing. I will also do the same thing to my West LA College class. So what I plan to do is this. On April the 1st, I'm sorry, not April the 1st, on March the 31st, March the 31st, it's a Cesar Chavez Day. So there's supposed to be no class also for them. But I told them the same thing. Hey, you know what? I will go over previous test too, right? So what I plan to do is with them, I will go over previous test tools that is different from your previous test two. You see what I mean? This way, then you will have at least 2 sets of previous test tool that you have access, you can see. I will make their recording available to you, and I will make your recording available to them. Do you see what I mean? Let's say for example, with them, let's say for example, with them, I will go over spring 19 math 227 test 2. And then with yours, let's say I go over spring 20 math 227 test 2. Okay, now you can see your own recording, right? Okay, but you cannot see theirs, right? Now I will upload theirs on YouTube so that you can see theirs, and I will do likewise on yours. Okay, now notice that these 2 days supposed to be the days that I'm not working. Okay, because they say no class, right? They give you a break, but it means also that I get paid without working. Okay, that's what it means though. But I will still go online to have some old tests for you available. Okay, now the thing is, like, on April the 9th, that's a spring break for us, right? So I don't think I will go on Zoom, but I think I will be available at home anyway. So if you have question, you can ask me during that time. And if we need to go on Zoom, well, then we go on Zoom. Okay, but unfortunately, our test 2 is April the 16th. It's basically already set in stone. Okay, I cannot move it, and I don't want to move it. We will be too far behind if I move it for another 1 week. Okay, now so instead of keep on moving the goalpost, instead of moving the test 2, I move the study instead earlier. Okay, so I did that April the 2nd next week with you. To at least to do the recording. Okay, now you don't need to show up, but if you want to show up, I still welcome you, of course, and you can ask question. Okay, now anybody have any suggestion what semester you want me to go over? I think I will go over spring 20 math 227 test 2. Let me make it available on this discussion board. Give me a second. So next week, we will go over, let me give you 2. So spring 19 and spring 20th. So you have material from others also. So spring 20th, that's for you. Where's that? That's spring 20th. And then spring 19. Is there any other semester you would like me to do?
Are you putting up test 1 or test 2?
Oh, yeah. Why do I put test 1? Thank you. Silly me. Thank you. That would be so silly of me. So test 2 instead. Should be test 2. So this is the test 2, spring 19 test 2. And then spring 20 test 2. So please, after today, before next week, please try to work on these sets, these two problems here, these two test 2 here. And then would you like to recommend one more? How about fall? Fall. I somehow think fall 19, I used the same question with spring 19. Let me go back even further. Maybe fall 15. Fall 15. No, I don't have it with me. Fall 17. Okay, fall 17, but it's not in PDF file. Give me a second. I need to make it into PDF file first. Now, this could be that fall 17 already have the solution on my website, but hey, it doesn't matter. Let's go over that anyway. Okay, this is good. So on fall 17, test 2. Okay, so now I have 3 different sets of test 2 that I plan to go over. Okay, not all 3 with you. I plan to go over maybe 1 or 2 with them, and then 1 or 2 with you. Is it okay? Then you just study from these 3 between today and next week. And if you, again, I will go over them next week. Okay, now hopefully, basically at least next week, by next week, we have 2 different sets that you can study from during the spring break. Okay, what happened, Melanie? I saw you notate something on my screen. Can you erase that for me?
Oh yeah, sorry, I did on accident.
Yeah, I cannot erase that, as I know. Can I? No, I cannot erase that. You have to erase that for me. Thank you.
You're welcome. Sorry.
That's okay. That's okay. Yeah. So that's the plan, our plan for next week. So this week we have to finish up to 5.3. Okay, which is very likely we can do. I even think that we have extra time actually. You know. Now let's start. And any questions so far? So again, next week I will go over some old tests that I post on our discussion board for today. Okay, but next week is extra from me. I'm not required actually to hold a class, and you are not required to come to class. So it's optional for you, and actually optional for me. But I just try to help you guys. Okay, I feel like they are paying me, but they don't require me to show up. You know, and it's like, hey, that's free money. No, I plan to be on go over those for like 2 hours, maybe 3 hours. And then after that, I will pack up. I go to Vegas. I get free room, by the way, from Phoenicia. Phoenician. I get free room for 3 days, 4 days. They insist me to come. And there's a blackjack tournament that they want me to join, but I say not on the dates that I want. So they end up putting me in Baccarat tournament. Well, anyway, that's what happened for next week. That's my personal story. Don't worry about it. Okay, let's go back to 5.1b. Now, what is 5.1? Last week, I hope you remember that 5.1 is on random variable. And we went over some material from last week. Let's see what we went over last week. I go to discussion board for last week. And we went over the definition of random variable, computing the mean and standard deviation from a probability distribution, right? Okay, now the thing is, for all these problems that we have here, or at least most of them, they give us the probability for the event, and all we need to do actually just to put them on probability distribution, and therefore we can compute the expectation. Okay, now what I will go over right now are questions that considered not easy. The foundation, the concepts already taught in the book, but our book itself never really put them together like what I'm about to do. Okay, what is that? Let's see the following question. Now, if you feel difficulty at this point for this question, you are very normal. For example, but I hope after I go over that, then you can understand also. Okay, for example, suppose a bus tour consisting of, let's say, 8 men and 12 women. Would select a group of 4 people of these 20 people to handle the paperwork of their journey. So imagine these 20 people, they go around, they go to zoo, they stay in the hotel, they go to museum, they go to eat, right? They need to do the paperwork, they need to pay this, they need to pay that. Then instead of all 20 people get involved, usually the staff of the hotel, they don't like it. They just prefer to deal with some people. So these 20 people decide, oh, you know what, let's just select 4 people from among us to take care of the paperwork. Okay, those who are very good in handling paperwork. Okay, now then the question then is like part A, construct the probability distribution of the number of women selected. So basically what we want to have is the probability distribution where X is the number of women selected, and then the P, the probability for that number of women selected. Of course, the total at the end has to be 1. That's what we want to do. Okay, now let's start with defining the random variable. Let X be the number of women selected. But Thomas, why do you single out women? No. We can construct probability distribution for the number of men selected. We can also do that. Okay, we can also do that. When we select 4 people from these 20 people, we have the sample space, but from that sample space, we can choose what to look at. And here, in this case, let's choose to look at the number of women selected. Okay, maybe after this, then I will ask you to construct the probability distribution of the number of men selected. Okay, but let's do the women first. Let X be the number of women selected. Okay, and we have 8 men, 12 women, right? We have 8 men and 12 women. We want to select 4 members from them. Okay, a total of 4. Now, the question is, how many women may be selected? What are the possible values of X, the number of women selected? Is it possible to have no women at all? Like all 4 of the men. If it is done randomly, yes, that's possible. So X may be 0. That's when all men, or 1 woman, or 2 women, or 3 women, or 4 women. It won't be 5, right? It cannot be 5 because you only select 4 people. Because we select only 4 people, then at most the number of women selected is 4. But Thomas, we have 12 women. That's true, but we select only 4, right? Okay, we select only 4, so at most we select 4 women. Okay, but it is possible that none of them women. What we will do right now, next, is to compute the probability for each of these possible value of random variable. So far, is it okay? We are not done yet. We are about to compute the probability, but I need you to understand, confirm that you understand that if we define X to be the number of women selected, then X may take values 0, 1, 2, 3, 4 only. Nobody say anything. I assume it's okay. Now then, I will compute the probability for each of them. Okay, let me start with probability that the number of women selected X is equals to 0. What is the probability that the number of women selected is 0? Now, if the number of women selected is 0, it means the other 4, okay, it's a group of 4, right? If none of them women, then the other 4 must be men. Okay, so what is the probability? That will be 8 choose 4 times 12 choose 0 over how many ways can we select 4 people from 20? That's 20 choose 4. Now, let me stop here, pause here, and ask you if you get how I get this, if you understand how I get this. Yeah, the denominator comes from the fact that of these 20 people, we will select 4. How many ways can you select 4 from these 20 people? That's the number of ways. Okay. Can we compute what is that number, Thomas? We can do it later. But at least right now, what I do is like we set up the plan. Okay, this is what we will do. The way we compute it will be 20 combination 4. Okay, now then, how many ways to get no women in that group? That will be 12 choose 0 times 8 choose 4. That's how we get that. Okay, now once we are done with that, we will compute that later on. Okay, I can compute it now. You can use your calculator to compute. 8 choose 4 is what? 8 choose 4 will be. Do you remember how to use combination? If not, let me know now. Don't wait until next week. The one I don't want is like somebody asked me silly question last minute. Like you're supposed to know that, like how to punch combinations, like even 2 weeks ago, not last week, 2 weeks ago, right? I thought that 2 weeks ago. Like 8 combination 4, I get 70. Okay, let me know if you try to do it and you don't get 70. Okay, 20 combination 4, I get 4,845. Yeah, let me know again if you don't get it yet. Yeah, if you have any last minute question, I would really hope that's a really good question, like a question that I didn't go over, or the question that I didn't go over, I went over but not really clear enough, you know, but not for this kind of thing. Like if next week or 2 weeks later you don't know how to punch combinations, you simply didn't study enough. I'm sorry with that accusation, but what other possibility, right? Something you're supposed to have known, and you have many chances to ask me how to do it, but you didn't ask, but you're like one hour before the test, Thomas, how do you punch combination again? Okay, I will still answer you, but I was like, okay, if you don't even know how to punch combinations, what you have studied so far, right? It tells me more about what you have not done than what you have done. Okay. Oh, as a big reminder, when you write combination notation, okay, the number to the left of that should be smaller and lower. The number to the right of that also should be smaller and lower. Okay, we call them subscript. Okay, the way I wrote it there. Don't write it like this. Don't write it like this. Don't write it like this. That's 8 combination 4, 12 combination 0. That's definitely wrong. Okay, I will penalize half point for that. Okay, some people even go to the extreme. They write the C as the subscript instead. They write it like this. That's actually a lot worse. No, that's not right. This is not right. Okay, the subscript actually for the numbers, the C is a capital letter, regular size. Now, let's come back here. The probability of getting no women, which means 4 men, is 8 choose 4 times 12 choose 0 divided by overall ways to select 4 elements from 20. 20 choose 4. Okay, now the rest basically computation. This will be 70 over 4845. I would just leave it like that for now. Let's focus on how to compute it. Okay, and probability to have 1 woman in that group of 4 will be, let's start with the notation. So 1 woman selected from in that group, okay, means the other 3 must be men. Right? Now then, what is the probability to have 1 woman selected in that group of 4 from this group of 20? The denominator will be the same, that's 20 choose 4. Okay, but what happened to the numerator? That will be 8 choose 3. That's the number of ways to select 3 from 8 men, times 12 choose 1. That's the number of ways to select one woman from 12. And after that, just to compute it, that's 672 over 4,845. Any questions so far? No question? Okay, let me ask you to do probability of getting 2 women selected from that group of 4. Write the notation only. Write the notation only. So you need 2 women, therefore you need also 2 men to be in that group of 4. Now, can you tell me what's the notation here? On the top? Okay, nobody say anything.
A choose 2.
A choose 2, that's right. That's for the number of ways we select men. And then
12 choose 2.
12 choose 2. On the denominator, we get
20 choose 4.
20 choose 4. That's right. Now, when we compute this, this will be 8 choose 2 is 4 times 7, 28 times 66 over 4845. 28 times 66 is 1,848 over 4845. Now, let me ask you to do the rest of those probability to get 3 women selected and probability to get 4 women selected. Write the notation. Always write the notation first. Okay, and then you compute. Yeah, for now, we leave it in fraction. Yeah, I believe it will be useful, helpful to visualize that by having this box here, to visualize it that way. Okay, okay, let me give you maybe 4 minutes from now to do this. So probability of having 3 women selected means 3 women plus 1 man. And the notation will be 8 combination 1 times 12 combination 3 over 20 combination 4. 8 choose 1 is 8. 12 combination 3 is 110 multiplied by 2, 220. So this is 4845. So the numerator will be 1760 over 4,845. Now, probability of getting 4 women will be, so 4 women implies only, implies no man selected. Okay, that will be 8 choose 0 times 12 choose 4 over 20 choose 4. 8 choose 0, I know is 1. 12 choose 4 is too big for me to compute mentally. That is 495. This is 4,845. So the probability is 495 over 4845. Okay, now we now get all the possible events, all the possible values of the random variable and the probability. Then we can set up the probability distribution now. with probability. So when x equals to 0, the probability is 70 over 4,845. When x equals to 1, the probability is 672 over 4,845. When x equals to 2, that's 1,848 over 4,845. When x equals to 3, the probability is 1,760 over 4,845. When x equals to 4, that's 495 over 4,845. Now, what we will do next is to add these probabilities. But they already have LCD. Let's just add the numerator. Okay, let's just add the numerator. So I will do this. I will add 70 plus 672 plus 1848 plus 1760 plus 495. Okay, I will add these numbers. Anybody can tell me what number do you expect to get when you add this?
4845.
4845. Why?
So the probability could be equal to 1.
That's correct. Okay. Now, so one way to check if we don't miss anything or we miscompute anything is to check the sum of this probability is supposed to be exactly 1. Okay. And I compute this and I get, yes, that's right. I get 4845. Let me make sure. Yes, I get 4845. So when I add them, I get 4845 over 4845, which is equal to 1. Now that confirms that I have a probability distribution. Is it okay?
You don't require for us to reduce those fractions.
I would like to, but let's do it later. Yeah, let's do it later. Actually, for now, I would just leave it like that. I focus on the how to deal with fraction instead. Okay, let's do part B. Let's do part B. Compute the expected value. The expected number of women selected. Or the average. Basically, if we repeat this experiment or do this over and over and over again many times, then on average, how many women will be selected over those many trials? Now compute the expected number. We will extend this table by px. Or multiply p by x, and then the sum that you have here will be your expected value. Okay, now of course I understand some of you, when you see fractions, you really kind of get scared. But let me remind you that when we compute fractions, let's say we have a times b over c, right? If we need to multiply a number, an integer by a fraction, that's actually the same to a over 1 times b over c. Therefore, that a multiplied with the top. Okay, you multiply that with the top. And just leave the denominator as is. Okay, so in this case, for example, 0 times 70, that's 0 over 4,845, or you can just simply write 0. Now, for the second row, probability x equals to 1 multiplied by the 1 times that 672 is 672 over 4845. Give me a second. And then this guy here, 2 times 1848. Then you use your calculator, right? Then you will get 3696 over 4845. Okay, and the third one, 3 times 1760. That would be 5280 over 4845. Okay, and then lastly, this will be 1980, I believe, over 4845. Any questions so far? Now then, the expected value later on will be simply the sum of these numbers. And again, because they already have LCD, common denominator, we just add the numerator. I get 11,628 over 4,845. So the expected value of x, which we can also write as a mu sub x or simply mu, is equal to 11,628 over 4845. Now at this point, if you want to make it decimal, go ahead. I get 2.4. Now, the reason I didn't want to do decimal earlier when it comes to the probability, because we are risking a rounding error here, 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 here. Even if you make it into 5 decimal places, there's a big chance that those decimals are very, very ugly decimal. Okay. And if so, we may have compounded rounding error later on, which is not good, right? And harder to compute actually, you know. Fractions are not visually entertaining, I know, but decimal will be worse because it seems like you are okay with the numbers, but the numbers already have some error involved in there. Okay, now that's the expected value. Let's continue with an variance. And its variance. Now, how to compute the variance? We do further extension for x squared and px squared. Okay, so x is 0 squared, that's 0. 1 squared is 1. 2 squared is 4. 3 squared is 9. 4 squared is 16. So I got them from here. I square each one of them to get me this. Now then continue. Probability multiplied by 0, that's 0. Probability multiplied by 1, 672 over 4845. Probability times 4, 1848 times 4, that is 7392 over 4845. 9 times 1760, that's 15,840 over 4845. 16 times 495 is 7,920 over 4845. So you see that I keep the denominator as is. And then I will add them. I get 31,824 over 4845. Now then the variance, therefore, variance of x is the first column, the first number, which is 1, times the third number, which is this, minus the square of this. I hope you still remember that from your test 1, right? Actually, from the second day of class. So this will be 31824 over 4845 minus 2.4 squared. Happens to be a nice number, so I will just use that number. Right? This is 2.4. Right? So then I use my calculator. Subtract it by 2.4 squared. I get 0.80842. That's the variance. So what happened to the standard deviation? And standard deviation will be the square root of that. I get 0.89912. Okay, now that's this example where I think the one that is difficult is to set up the probability distribution, because it requires us to remember what we learned from the end of chapter 4 about the combinations, right? Technique of counting techniques, okay, to get that probability distribution. The questions we have from the past, from last week, they always give us the probabilities such that we just need to set them up as a distribution. Right now, we don't even have the probability. We need to compute the probability ourselves. Okay, but we are going to do, from what I teach you, I believe you can go pretty far. And therefore, I don't want to say, I don't want to let you think that, hey, you know what, you cannot do this, you cannot do that. No, actually, the foundation I gave you is good enough to do this far. Okay, now what we have done here, however, let me go back a little bit. What we have done here, however, is the topics or the concepts that not a lot of students know, because not a lot of instructors actually told them to do this far. Sometimes I think this way, like when an instructor refuses to ask a certain question that's the student supposed to be able to do, it's either the instructor don't want to make it hard on students. Okay, that's the way they think though. Okay, or most of the time that's because the instructor thinks that their students cannot do that. Okay, but imagine if a teacher say this to you, like imagine if I say this to you, oh, you know what, we will not do that because I don't think you can do that. No, let's not doing this because I don't think you can do it. What do you feel? Honestly, I feel offended. If I were the student, I feel like I degrade my students. I talk down on my students as if like they cannot do anything. Now, if my students still cannot do anything while they're supposed to know how to do with this material, I basically look down on them. No, right? You see what I mean, right? So no. That the reason I say that, you know what, don't be afraid with these hard questions, okay? Because I know you can do it if you study, of course. Now, of course, if you don't study, then trust me, even if I make it easy, you still cannot do it. Okay, I have seen that enough. Okay, I've seen that enough, and I have many friends at West LA College, East LA College. We share each other about our stats class, and you can see students who claim that they're already at UC Irvine, UC Riverside, and they take statistic with us. They end up failing anyway. Why? Not because they are not smart. The fact that they can go to UC means they have the brain. Okay, well, but what we need are people who use their brain, not simply having their brain. Okay, so use that. That's the difference between being smart and being wise. Okay, we need both. Okay, we need both. Now, let's create another problem. Let's create another problem. Or yeah, let's create another problem. Doesn't have to be exactly that one. And I would like you to do this problem. At least create the probability distribution. Okay, let's start with a city council consisting, let's say, 5 men and 7 women, decides to form a committee of 3 members. Okay, what I want you to do is construct the probability distribution for the number of councilmen selected. To that committee of 3. Yeah, let's do this one first. So for the expectation and variance and therefore standard deviation, we can do that later, but at least you know how to set up the probability distribution. I want you to do this. I give you the setup, the early setup. Let X be, so we define the random variable first. Let X be the number of men selected. Okay, then X will be maybe 0, all of them women, or 1 man, or 2 men, or 3 men. Okay, and you will compute the probability for each of them. Then write them, organize them into a probability distribution. Okay, to give you a background, maybe not really a background, to give you some thought on this, some context or relevancy on this. We can change this instead of city council. We can change this into a Senate. The Senate consists of, I think right now we have consists of 50 Democrats and 50 Republicans. And they decide to form a committee of 10 to investigate, if we want to be political, to investigate the January the 6th situation in Capitol. Okay, now then construct the probability distribution for the number of Republicans selected to that committee. You see, it's actually just the same. Okay, oh, of course, larger number, right? But that's just the same idea. We just change the number, we change the situation, but the underlying concept are exactly the same. And the case where that happens in one city council somewhere in, I think San Bernardino County or Orange County. I think San Bernardino County. So there's a city there, consists of course, like I think around 8 city council members. They want to decide if they want to keep their city like an old city and attract tourism that way, or they want to develop that city with some malls, more streets, make it moderize the city. Okay, so then when they look further, they found out that of those 8 people, 3 of them actually more traditional. They're on the conservation side, not conservative. I'm talking about these people. They tend to keep the city as is, and the other 5 tends to be the one who wants to improve, modernize the city. Now, if they form a committee of 4, what kind of decision possibly made by these people? Okay, so you see, suppose I come back to this question. Okay, suppose I come back to this question. We have 5 men and 7 women decide to form a committee of 3. A committee of 3 for what? Let's say for women empowerment for that city, because they think, you know what, we have more than half of the city residents actually women, but women economic activity, their education are not as improved as the male counterparts. So let's see what we can do. Let's start with forming a committee of 3. Now, if you have committee of 3 for women empowerment, for example, you would like women in that committee, right? But forming a committee of 3 and you require them to be women sounds sexist by law. So they're supposed to do it by lottery, supposed to be, right? Okay, now then, before that happens, you start doing this computation. What is the chance that all 3 of them are men? Like, and it sounds really bad if 3 men form is in the committee of 3 for women empowerment. What do they know about women? Right? Okay, but deciding that all of them have to be women also, that's also not really, how to say it, for some people it may be sexist. You see what I mean? Okay, for some people, so they still have to do it by lottery, but they all of them pray that we hope that we have more women to be more representative of women's few women's aspiration in this committee. Okay, now can you now compute that probability distribution? Okay, I'm just, in this example, I only give you, okay, do this. Okay, we have this situation, select committee of 3, construct the probability distribution. Okay, how we will use that, I can put more storage into that, right? But can you do this first? Okay, let me give you how many minutes? Maybe 10 minutes for this? Maybe 10 minutes? Okay, right now it's 9:25. I will come back at 9:35. Okay, and don't feel bad if you get stuck. Don't feel bad if you get stuck. You can kind of like think about, I hope you take notes. You can think about what we did earlier. But basically, you end up with this. You will have 5 men and 7 women. Okay, and then let's say you want to select 1 man, 1 woman, then there must be 2 men there. Now, how to compute the probability? Okay, basically what you need is to find probability that x equals to 0, probability x equals to 1, probability x equals to 2, and probability that x equals to 3. Now, after you're done, you set them up in probability distribution. Okay, let me ask you to start working. I don't think it is possible. I should not say I don't think. It is possible that you cannot finish in 10 minutes. Don't feel bad about it. Okay, but I would like you to do most of that by that time. Okay, go try. So we have 5 men and 7 women. Probability of no man. So man is 0. So it means 3 of them women is 5 choose 0 times 7 choose 3 over 12 choose 3. I will compute that later. The probability to have 1 man will be, this is 1 here, means the other 2 are women, because they need a community of 3, right? A group of 3. So that will be 5 choose 1 times 7 choose 2 over 12 choose 3. Probability to have 2 women, 2 men, X is for men, right? 2 men will be 2 men, therefore 1 woman. That's 5 combination 2 times 7 combination 1 over 12 combination 3. And finally, the probability to have 3 men means 5 choose 3 and no woman, 7 choose 0, 12 choose 3. Okay, now I will compute each one of them. 5 choose 0 is 1, I know. 7 choose 3 is 35. 12 choose 3, I think 220. That's 35 over 220. Next, 5 choose 1 is 5. 7 choose 2 is 21 over 220. That will be 105 over 220. 5 choose 2 is 10. 7 choose 1 is 7. So this is 70 over 220. And the last one, 5 choose 3 is 10. 7 choose 0 is 1. That is 10 over 220. So if I put them together in a probability distribution, I plan to extend this anyway later on, so let me just make it big. That's x equals to 0, 1, 2, 3 with probability 35 over 220. 105 over 220, 70 over 220, and 10 over 220. Now, if you want to do the reduction, reduce these fractions, do not reduce that all the way down. Take a look on what common factor do they have. Okay, I will reduce by 5 because all these numbers here has common factor 5. Okay, 35 has 5. Okay, 220 has 5, 105 has 5, 70 has 5, 10 has 5. Okay, so I will reduce by 5. The reason is I want to keep them having LCD, common denominator. Okay, so if I reduce by 5, that will be 7 over 44. Reduced by 5, that will be 21 over 44. This is 14 over 44. And this is 2 over 44. Reduced by 5, right? And the total will be 44 over 44, which is 1. So it is a probability distribution. Okay, so if my question only construct the probability distribution, then we are done. Okay, now suppose we want to go on to compute the expected value. To compute the expected value, then I will do Px. That's 0 over 44, 21 over 44, 28 over 44, 6 over 44. How do you get those, Thomas? I multiply the x by the numerator over 44, x by the numerator over 44, x by the numerator over 44. That's what I did. And then when I add this, I wonder what's this? That's 55. Yeah, 55 over 44. That's 5 over 4, which is 1.25. So the expected value, okay, the number of men in the committee of 3, in this case, will be 1.25 on average. Yeah, if you do this experiment or do this selection many times, then on average, you end up with 1.25 men in the committee. Now, if I go on further to find the variance, means I extend the table even further. So x squared 0 here, 1 here, 4 here, 9 here. I wonder if you are following me. If you write it in, if you follow me in writing. Now I will continue. Okay, so multiply by the probability. Of course, this is 0. Multiply probability, 21 over 44. Multiply by probability, that would be 56 over 44. This is 18 over 44. If I add them, what will I get? 74, 95 over 44. So the variance is 95 over 44 minus 1.25. Oops. 1.25 squared. 95 over 44 minus 1.25 squared is 0.59659. Therefore, the standard deviation will be the square root of that, which will give us 0.77239. Okay, I know this part is not easy, and to make it worse, we don't really have this part in your textbook. But that's why I need to go over some of my old tests and show it to you so that you have more examples from my old tests. Okay, yeah, next week I will go over my old tests, and in my old tests, I think in pretty much almost all my old tests, my previous tests, I have 2 questions similar to this usually. Okay, one of them on the easy side, explicitly asking for this kind of situation, and another type of question have the same underlying concept, which if you think about it is basically this one. Okay. Yeah, I finished the material for 5.1 from textbook last week. Now, together with this, then you have a more complete view of how to compute probability and construct the probability distribution and find the expected value and variance, therefore standard deviation. Now I will go on to 5.2. 5.2 is one of the special probability distribution. 5.2 is binomial probability distribution. Now, it must be in my lecture, the video lesson that I asked you to watch. Okay, but let's emphasize what kind of situation that gives us binomial distribution. Okay, to be binomially distributed, a random variable must satisfy all the following requirement. The first one, the number of trial n is fixed. Yeah, I will put an example on the right-hand side here. For example, a very standard example of binomial distribution is the case when we toss a coin. Let's say we toss a coin 10 times. Okay, so this is one experiment with 10 trials. Okay, so this 10 times here, this 10 is the number of trials. Next, the outcomes of each and all trial, each and every trial, are either success or fail. That's the most common terminologies they use when they introduce binomial distribution. But it's actually more into that the outcomes has to be only 2 possible outcomes. Okay, there are 2 outcomes. Maybe I say it like this. There are only 2 outcomes for each and every trial. Okay, most of the time, most textbook, if not all, use the term success or fail. But it's actually not success or fail only. It's either yes or no, open or close, or in this example for coins, it's head or tail. A boy or girl, female or male, right? What else? Green light or not green light, a pass or fail. What else? Republican or not Republican, Democrat or not Democrat. I do not want to use Republican, Democrat because we have the third party. Okay, it is possible somebody not Republican, not Democrat. Okay, so using this is actually not a perfect binomial. Republicans and Democrats, for example, not a perfect binomial. Okay, because we have Green Party. Okay, for example. Okay, we cannot use green, yellow, red, just like in our traffic light, but we can use green or not green. Okay, green or not green. You see? Okay. And so on and so forth. So it's not limited to only success or fail. Okay, when you toss a coin, in this case, you have the possible outcomes, head or tail. Okay, now then the third one, the probability of success. I use the word success here following our textbook and a lot of other textbook. The probability of the success is constant throughout the experiment. Throughout the experiment. Let's say in this example here, probability of getting ahead is 0.7. Okay, now I didn't say it's a fair coin. Okay, I didn't say it's a fair coin. And it doesn't have to be a fair coin. For us to have binomial distribution, doesn't have to. Okay, now probability of getting ahead is 0.7. And this 0.7 will be the probability of getting ahead for all 10 times we toss a coin. Okay, now on the top of that, we also need to emphasize that the effect are independent of each other. What does it mean, Thomas? It means the probability of me getting, we tossed a coin and getting a head right now will not change regardless how many heads happened before. So let's say I already tossed a coin. I get tail, tail, tail. What is the probability the next one is head? It's still 0.7, but Thomas, we have tails already. Okay, don't you think it's supposed to be tail again? Well, according to this binomial distribution, no. Regardless what happened in the past performance does not is independent of, does not influence the future performance. Okay, so knowing that we have tossed 3 tails, for example, doesn't tell me anything more or less about the probability of getting head again. Now, the fourth requirement is we are interested in the number of successes only, regardless the order. Okay, I believe I mentioned this requirement for us to form binomial distribution in my lecture. Okay, and I repeat it again in this discussion to make you aware that for us to know that a certain random variable behave binomially, it must satisfy all these 4 requirements. Okay, now suppose we toss a coin 10 times, probability of having a head is 0.7. We are interested in the number of successes only. Like say, for example, find the probability of getting, let's say, 4 heads. Now, there are many ways to get 4 heads out of this 10, though. Okay, you may have head, and then the rest are tails. Okay, now you may have tail 6 times first, and then head 4 times. That's possible. We may have head and then tail and then tail and then head, tail, head, and then tail like that. It's possible. Okay, now, but we don't care about the order. All we care is what is the probability of getting 4 heads. Okay, now, please don't just think that, oh, it only applies for coins, Thomas, and I will never deal with coins for my work later on. No, that's not true. In fact, binomial distribution is the second most oftenly used distribution in our daily life. The second, not the first. The most frequently used probability distribution in our daily life is normal distribution. The second most often is actually binomial distribution. Okay, regardless your major. So you need to know this not only to pass this class, but also for the purpose of your real life, like applying to your real life. And of course, if you don't understand this, you will never apply that, and you never think that you can use this, right? And I can change this, toss a coin 10 times instead, and change it into like, okay, select 10 people. The probability that person already vaccinated is 70%. Now, if you select 10 people at random, what is the probability that 4 of them already vaccinated? Okay. Or you have a family of 10 children. The probability that to get a girl is 0.7. What is the probability you have only 4 girls in that family, siblings of 10? Okay. Of 10 students, 70% of them California resident. Okay, what is the probability of 10 students you randomly selected, 4 of them California residents? Or let's say of 10 voters, probability that person will vote for Democratic candidates is 70%. What is the probability you end up only 4 of them selecting a Democratic candidate? See, it's actually just the same underlying concepts, right? Okay, now, notation. If X is binomially distributed, then it will be denoted this way. N, squiggle, up first and then down, B, N, P. In that order. The N is the number of trials. The P is probability of each success. So if we look back here, and this X here, let X be the number of heads, then X will be binomially distributed. Number of trials is 10. Probability of each getting a head is 0.7. Okay, memorize this notation. I'm not trying to make your life harder. Okay, it is actually easier if you see it this way. Okay, we can have so many possible cases, right? Toss a coin 10 times. You have 10 students. How many of them California resident? You have 10 voters. How many of them vote Democratic candidates? You go to a store 10 times. How many times you go there in it's open. Actually, the one that I would like to do is you go to American Red Cross 10 times. Okay, the probability that they don't have enough space to take your blood is 70%. What is the probability that you go there 10 times and 4 of them you drive home without a chance to donate your blood? This becomes an issue for a lot of blood donors, by the way. The one I just said. Okay, why? Because of the restriction we have, the social distancing. Then I think I told you before that I'm a blood donor. I am actually a platelets donor. I donor platelets. Okay, now I may already have appointment with them, but they always purposely overbook. And I understand they purposely do that. Overbook means like this: they only have 6 spots available to for donation. Okay, but they register 8 people because they expect there's a chance that some of these 8 people actually suddenly get sick or cannot come for one, or I mean they are donors anyway, so they are not getting paid. They don't have the obligation to show up, and especially because more into they possibly suddenly think that they are not feeling that healthy, right? So they usually overbook normally. That's what I will do if I were them. I'm not trying to talk shit about American Red Cross. No, I mean, that's what they do. That's what they're supposed to do. If I were them, I will do the same thing. Okay, but then that makes some people get disappointed. They already get prepared. Prepare in a way like this. Like suppose I want to donate blood right now, today, then at least 2 days earlier, starting from Wednesday, I start hydrating myself more than usual. I need to drink a lot of water. Okay, I need to drink a lot of water. Why? Because you want to make your blood vessel to enlarge. If you are not well hydrated, then your blood tend to be thicker and your blood vessel tend to be smaller. So it's kind of like harder to poke your vein. Okay, and after we poke it, your blood is too thick that it's so hard to take your blood out. So to prepare ourselves to have platelet donation, the preparation is actually around 2 days in advance. Okay, let me share with, I really want to share that with you. I want to share that with you. Okay, this is recorded. This is the time for me to share with you. Okay, why I am so into American Red Cross platelets donation chart. Is it the chart? Maybe just platelet donation. Now, I want you to realize that platelets donation, donating platelets, is not the same to donating blood. It's not the same to donate blood. I would like American Red Cross picture. Any American Red Cross picture? Most of them actually not from American Red Cross though. Ah, this one. Hey? Where's that? This is from American Red Cross. It's not like a regular blood donation. It's just like 15 minutes, they get 1 pint of your blood. Okay, no. This person will get poked, most of the time will get poked at 2 different places. First, the blood coming out, and then second, the blood coming in. So in this case, for this lady, the blood coming out from the right hand, go into the machine. Okay, they separate your platelets from the rest of your blood, and then they take your platelets, but they put something to your back to your blood so that you are not losing too much volume of water, too much volume of your blood, and then put it back through the other arm. Okay, now I usually donate 3 units of my platelets, means they consider that 3 doses. Most people get only 2. Most people, they can donate only 2. Some people actually get 3 also. Now, because I donate every time I get to this chair, I can get 3 units, then they prefer me to be the one get to this chair. Now, the thing is, once they poke me and strap me to this chair, I will stay here for 2 hours. Okay, I will stay here for 2 hours, and this is a sad thing. Okay, your right hand here has to be keep on pumping. You see these balls here? Okay, now she will be pumping this hand basically every 5 seconds for 2 hours. Yet the left hand cannot move at all. The left hand cannot move at all. Okay, now what happens if you move that left hand? Let's see. Platelets, donation, bruise. It looks like this. And sometimes you just don't remember which hand you need to pump, like you stay there for too long, right? And then you kind of like space out a bit, like a bit sleepy, and then you end up pumping the left hand instead of right hand, let's say, for example. Okay, or something so itchy, your nose is so itchy that you cannot hold it, then you end up scratching your nose using the wrong hand, you see? Okay, and it will stay like this for at least 2 weeks. It can be really bad though, like this. You see this one? It can be really like, you see. So people who donate platelets, okay, that's including me, proudly say, okay, are heroes. Why? They sacrifice themselves. They need to drink a lot of water 2 days in advance, yet on that day, they cannot drink. Yet on that day, they cannot drink. Why? Because they will be strapped on that seat for 2 hours. And if they drink too much that morning, they need to hold their PP for 2 hours. Not to say that after you're done, they still need to slowly pull this out, pull this needle out, and then clean you up, make sure you are safe, that when you go to restroom, your blood is not leaking from your vessel, from your vein. You see? So being platelets donate platelets is not a little stuff. Okay, we are actually fighting for life. Especially if you already have immunity from COVID, they actually value you more, which means you already have the antibody from COVID-19. Okay, they will call you all the time. They need you. Okay, the thing is, like, out of 100 people, out of 100 people in our society, only 2% actually donate blood. And of this 2%, only like around 15% donate platelets, while the number of people having cancer are a lot. They need platelets. So unfortunately, I cannot give you extra points for donating blood or donating platelets. If I can, I would, but no, I'm not allowed. By law, that's not allowed. Okay. I hope at least by sharing this with you, you understand that people, if possible, please consider donating blood and try to inquire about donating platelets. Okay, people who donates blood and platelets regularly tend to be healthier. They tend to be healthier. But not because when you donate blood, you are healthier. No, it's because you know you will donate blood, donate platelets, then you keep yourself healthy so that you can keep on giving. Then you start thinking about, you know what, if I eat this too much, if like me, if I eat Korean barbecue too much, then my blood tend to be fatty, okay, and that will not good with the quality of platelets I give around 2 weeks from now. So I go to Korean barbecue, right? But I will not do that every week, no. Okay, so if I have a party, let's say this Friday, Korean barbecue, I will not go with the next 1 week. Why? Because 2 doses of Korean barbecue in 1 week will be too much for my blood. Okay, it's still okay for me. I will still be healthy, not too much. Just don't do it too often. Okay, but the quality of my blood already compromised, and the receiver of my platelets may not benefit as much as they expect. Okay, so you see, you can say that you will contribute to your society once you get richer. Actually, no, you don't need to be rich to contribute. People who helped me in my life during difficult time of my family, during my difficult time, I can say none of them actually rich. They just have the heart to give. And if you don't have money to give, consider giving your blood. Okay, again, if I can give you extra credit for that, I will, but I cannot. Okay. Beside donating blood, donating platelets, I also volunteer with American Red Cross as a driver. So I drive your blood. People who donate blood, okay, I drive their blood to hospitals that need the blood. Okay. So instead of being the person who need it, maybe your family members later on need it, how about be the person who deliver that? Okay, I'm not saying that deliver the blood like as a driver. No, instead of being the receiving end, how about being the giving? Okay, and who knows? Karma is there because you help other people in their healing process. There, when you need such luck, you also have it, right? To be honest with you, I don't believe in karma. Okay, I don't believe in karma. That's me though. My wife is very believe in karma. Okay, but even though I don't believe in karma, I still live as if karma is there. Okay, I still give as much as I can to my society, give back. I give my blood, I donate my platelets, I still donate money also. And I'm proud when it comes to that side of my life. I'm proud to share that with you. Okay, there are parts of my life that I'm not proud to even mention. I'm embarrassed of myself. Okay, like one of them is like being a gambler, right? Being a gambler, that's not something I want my son to do. Okay, I can share that with you because I want to show you that I apply my statistic, right? But that's not something I want my son to do. Okay, but the fact that I donate platelets, I many times when the social distance is not required, I actually brought my son together with me. So he saw what I did. And my son asked me, Dad, what are you doing? Oh, I give my blood. Oh, why do you give your blood? Well, because somebody needs it. Okay. Then he knows that that's one way for us to share with our society. Okay. And I hope you too. Okay. And no. Yes, for statistic, you may need to study harder, but to be a reasonable part of your society, you can give part of your life back by giving blood. Okay. Now let's come back here. Now, in this question, we want the probability to have 4 heads. That's the notation. That's the probability notation. Okay. Now, the probability to get 4 head, that's the probability notation, will be followed by probability the calculator notation, binomial Pdf. I will show you later on calculator. Okay, but binomial Pdf followed by 10, 0.74. Now let me explain to you this notation, and I will show you how to use calculator after this. Okay, binomial Pdf, why Pdf. If you see on your calculator later on, you have Binomial Pdf, you have Binomial Cdf. You use Pdf if you just want equal sign. If you just want the probability of 4 successes, then you use Pdf. The first 2 numbers follows these 2 numbers. That's why I need you to memorize those notation. Okay, not simply because I want you to make me happy. No, I have my reason. Okay, now then, this 4 here is the number of successes you want. That's Binomial Pdf. Now let me show you with the calculator. How to get to that Binomial Pdf. So you need to go to the list of distribution, and the list of distribution is here. Okay, above the fars, the blue color. If you have physical calculator, it's usually in yellow. So you go to second distribution. What is this? Okay, second distribution. Oops, no, that's not what I want. Yeah, second distribution. Let me repeat again. Second distribution. Okay, and then go down, 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 down. You see Binomial Pdf and Binomial Cdf. You choose Binomial Pdf. Binomial Pdf stands for Binomial Probability Distribution Function. Cdf stands for Cumulative Distribution Function. Okay, we need the P1, the Probability Distribution Function. Enter. Now TI-84 usually guide you. Okay, what is the number of trials? In this case, 10. What is the probability of each success? 0.7. How many successes you need? 4. And paste. Now, the notation I show you in writing earlier is basically this notation that you need to write. Binomial Pdf, the first number is 10, the second number 0.7, and the last number is 4. And then you press enter. That will give you the probability to have 4 successes, 4 heads in that situation. Okay, so this will be 0.03, 0.036756, so 676. Okay, that's for Binomial Pdf. Now, I would like you to replicate what we do in the following example. Let's call this example 2. I will stick with notation only for now. X is binomially distributed with n equals to 8 and p 0.4. Now, I want you to compute a px equals to 3. So if you have 8 trials, probability of success is 0.4. What is the probability you have 3 successes? Okay, that's for part A. Part B, how about probability of x equals to 5? How about part C, probability that x equals to, let's say 4? Can you do that? Let me give you 3 minutes for that. Okay, so you can replicate from up here. Okay, let me give you 3 minutes for that. That's the 10:21. You know what? Let's take our break also at the same time. So instead of 10:21, we come back at 10:30. Okay, we come back at 10:30 with these 3 problems done with the probability. We have the probability notation there. I need you to write the calculator notation, then the answer. Okay, so probability notation, calculator notation, and the answer. Okay, Now we come back at 10, make it 10:32. Okay, see you later. So let X be binomially distributed with 8 trials, probability of each success 0.4. Then part A, what is the probability that we have 3 successes? That will be binom Pdf 8, 0.4, 3. Then I use my calculator. Let me share the whole thing with you. Then that will be binom. Give me a second. Binom Pdf. I really wonder why this shows up there. I just hate it to be there. Okay, binom Pdf, scroll down. So binom Pdf. The number of trials is 8. The probability of each success is 0.4. And the X value is 3. The number of successes is 3. That's the coding. This is the probability. That's 0.27869. 0.27869. That's the probability to have 3 successes. Is it right? That's 3 successes, right? That's right. Now, how about if we want to have 5 successes? Then again, binom Pdf. The number of trials is 8. Probability of each success is 0.4. The number of success is 5. Okay, but in my test, I need you to write the calculator notation first. Okay, so this is binom Pdf 8, 0.4, 5. And that gives us, what's that? 0.12386. How about the probability of having 4 successes? The calculator notation, binom Pdf 8, 0.44. Using our calculator, let me just change this. So I change the number of successes to 4. I get 0.23224. 0.23224. Okay. Now, let me go lower, to go below this. Okay. Now, what happens if I need probability that X is at most 3? At most 3. You see, we have 8 trials, right? We have 8 trials. So the number of successes, it's either no success, 1 or 2 or 3 or 4 or 5 or 6 or 7, possibly all 8 successes. Okay, now when we say at most 3, it refers to the situation up to 3. Up to 3 successes. Let me actually move this picture here. Up to 3 successes. Now then, while the rest, like for example, the first one here, probability of 3 successes, exactly 3, only 3 successes. You just need the probability of 3 successes. Like if you toss a coin 8 times, the probability of getting a tail is 0.4. the probability of getting 3 tails is this. That's the probability of getting 3 tails. Okay, now question D is not probability of getting 3 tails, but the probability of getting at most 3 tails, maybe 0, maybe 1, maybe 2, maybe 3. Okay, now in that case, we will use Binomial Cdf. Now, Cdf stands for cumulative distribution function. Okay, cumulative distribution function. Okay, if they use equal sign, you use Pdf. If it use less than or equal to, then you use Cdf. And this will be 8, 0.43. That's the probability to have at most 3 successes. How to use calculator? That will be Binomial Pdf, right below Binomial Cdf, which is right below Binomial Pdf. Binomial Cdf, okay, number of trials here is 8. Probability of each success is 0.4. The cumulative up to 3 successes. And that will be 0.59409. 0.59409. Now, let me ask you to try this. Part E, what is the probability that the number of successes is at most 5? Can you write down the probability notation and compute that using your calculator? Now, that will be Binomial Cdf 8, 0.45. That is, if we use our calculator, that's Binomial Cdf. Number of trials is 8, probability of each success 0.4, and cumulative up to 5. That's 0.95019. 0.95019. Okay, and 5 or less than 5, from 0 up to 5. From 0 up to 5. Now I will do more variations from here, but we get the foundations already. Now let's change to part F. Let's say, what is the probability of getting less than 7 successes? Less than 7 successes. Less than 7 means up to what? So 0, 1, 2, 3, 4, 5, 6, 7, 8, right? Okay, less than 7 refers to up to 6 only, right? Up to 6 only. Now, let me write down what's the probability notation adjusted. So probability that X is at most 6, such that you know when you use your calculator, okay, the calculator notation will be Binomial Cdf 8, 0.4, up to 6, not up to 7. Less than 7 means up to 6 only. the number of successes to be less than 7 in this case, then only up to 6. Okay, then from there you use your calculator. Okay, using calculator now is supposed to be an easy stuff for you. Okay, you do it yourself. Okay, G, how about you do this yourself? Probability that X is less than 3. What is the adjusted probability notation and calculator notation, then the answer. Okay, let me ask you to do this in maybe 1 or 2 minutes. Try it, please. Okay, the earlier I compute using my calculator, I get 0.99. Oh, where's that? 99148. That's for probability that the number of successes is less than 7. Probability that number of successes X is less than 3 means it's only up to 2 successes. That's Binomial Cdf 8, 0.42. Okay. You need to know the notation. Okay, pay attention to details. Okay, pay attention to details. Now then, I use my calculator here, Binomial Cdf up to 2. Let me just copy the N3, but change that up to 6, now up to 2. That's 0.31539. 0.31539. Let me make sure that I copy that right. That's right. Okay, is that all, Thomas? No, we have more variations. The one on the left-hand column are the basic ones that you really need to know before you go on to the right-hand column. Okay, the right-hand column, you need to do some adjustment. Now, why do you need to do adjustment? Here's what happened. Your calculator can only handle 2 cases. The case of equal to, that's when you use Binomial Pdf, and the case up to, that's when you use Binomial Cdf. In other cases, you need to do adjustment. Okay, one of them, the one you saw earlier, actually instead of up to, it's less than 7, less than 3. What if we change the question to be, let's say part H, what is the probability that X is at least 4? At least 4. Let's take a look at the situation. The number of successes possible are from 0 all the way to 8. Why up to 8, Thomas? Because we have 8 trials, so we may have 8 successes in total, right? Okay, now, however, when we say at least 4, it refers to the situation starting from 4 and on. Now, the thing is, our calculator don't have any function for this. They have only the functions on the left-hand side, the PDF and CDF. They don't have any function for this. What we can do, however, is dealing with the complement. We can compute the complement. Okay, we can compute the probability of the complement using the calculator function, right? So instead of attacking that probability X at least 4 directly, we use the complement. That's 1 minus probability that X is at most 3. Why is it at most 3, Thomas? Well, look at the situation here. If you need 4 to 8, then the complement must be up to 3. Right? That's the complement. Now then from there, You go to your calculator notation, right? That's equals to 1 minus binom Cdf 8 0.43, which we happen to already compute it in part D. 1 minus 0.59409, which will give us 0.40591. Okay, now the key is here. Trust me, this is very, very helpful. This is very, do this sketch. Do this sketch. Okay, either on your side note or on your scratch paper when you do this. Okay, the one I would like to see, I want to see are these. This is the ones I need to see. Okay, now usually because that's the one I need to see, that's the one you try to provide me, and because I don't need to see this, you don't do that at all. No, no, no. If I were you, I will do this. Okay, trust me. I will have to answer those kind of questions again and again. Thomas, why is it at most 3? Thomas, why this? Thomas, why that? But that's simply because that person is too lazy to set this up and try to visualize it themselves. Okay, do it. This is for you though. Okay, the reason I use this to illustrate is because I have a student in the past say that it is very, very helpful to do this, Thomas. Okay, I did this, but many, many years ago, I tried to make my students just to visualize it themselves until a student say, Thomas, I can't visualize that. But then my tutor told me that's what that guy say. My tutor told me, try to do it this way. And it turns out to be very helpful. So that tutor share with his student, that student share that with me. That's what I share with you. Okay, this is not from Thomas. And there's no point for me to take a credit that belongs to a student, that belongs to a tutor. Okay, simply because it's helpful for my students, then I share that with you. Doesn't matter who takes the credit. Okay, but because it is useful for you, why don't you do that? Okay, please do that for yourself. Okay, do that for yourself. Now, let's go on to the real binomial distribution problem. What we did here are just notation. It may confuse you. I know. Thomas, I want to see the real word problems. Well, if you don't even know the notation and how to conduct the computation, then going to a real life situation right away does not help. We have schools for that reason. We go to college for that reason. College, just like schools, supposed to be a little lab for us to experiment this and that. Okay, but if you cannot formulate the situation correctly, then exposing you to real life situation right away may confuse you instead. Okay, so why a lot of students, not only you, a lot of students have that syndrome that, Thomas, when I do word problems, I get confused. Well, because your theoretical foundation is weak. Okay, but why your theoretical foundation is weak? Because when I did it theoretically, you keep on saying it has nothing to do with my life. Okay, no, it's not. It has something to do with your life, but to make you mature to face life situation like word problems, then I need to train you with the theoretical foundation first. Okay, now let's do problems for real life situation. Let's say, for example, let maybe a survey is conducted on let's say 12 randomly selected students. A survey is conducted on 12 randomly selected students. And let's say we want to talk about vaccinated, okay? Probability that a student has been vaccinated is let's make it 0.2, still low. Okay. Now I'm not saying that this number is bad. This number is actually pretty good right now. Why? Because this is a student. This is not somebody who works in medical field yet. If you are in medical field, then everybody should be vaccinated by this point. Okay, as educators, they are still working on educators right now, and of course, people who are 50 years old or older. Okay, but starting from April 15, as I know, it will be open for public. April the 1st, they basically face it with more and more people included. Okay, of course they prioritize some people, right? As supposed, but I heard that starting from April 15, California vaccination program will open for everybody. Okay, so at this point, if you're a student, I will be happy enough if 1/5 of you are vaccinated. Okay, if you're a medical workers, like a doctor, a nurse, right? Even for receptionist of a medical office, you're supposed to be vaccinated already. Okay, for that, it's supposed to be already 100%. For educators, as I know, at this point, they're still working on that. So the numbers around 40% to 50%. Okay, not every educators get vaccinated yet. Not to say that there are some people still question the effectiveness of the vaccine. Okay, yeah, with me, I'm not vaccinated yet. I'm for vaccine though, don't get me wrong. I think I mentioned this before. I'm for vaccine, okay? But when I try to register, it's so full, and most of the one who really need still are, like, I live in Monterey Park. Like, I live on Freeway 10 and Atlantic, so very close to East LA College, right? Okay, and in LA, in our Monterey Park, we have three, I think, like around three communities of seniors, like 3 senior housing, and not all of them get vaccinated yet, and they themselves, like these older people, senior people, they have hard time to have to go to that place to get vaccinated, you know. So when I want to register, I don't get the spot. When they say it's open, I actually chase my computer, and it turns out that now the time that they are available, the time that I need to teach, the time that they are not available, when I'm available, they don't have that such space, you know. So well, but anyway, it means somebody else get the spot instead of me, which is okay. I'm not going out a lot anyway. Okay, but I want to get vaccinated, you know, but I'm not putting it as a priority compared to other population who is not who needs that more. Okay, now suppose we have that. Okay, and then the question will be find the probability that. So find the probability that part A, let's say 5 of them, 5 are vaccinated. And part B, let's say probability that 7 are vaccinated. So I want you to write the probability notation, and then calculator notation, and the calculator result. Okay, I will start with this. Let X be the number of students vaccinated. So this X will be binomially distributed. Number of trials is 12. Probability of each success is 0.2. Now then you compute what is the probability, 5 of them vaccinated, 7 of them vaccinated, probability that at most 6 are vaccinated. Let's say part D here. Less than 3 are vaccinated. And then part E, more than 7 are vaccinated. Let's answer these questions. Okay, I will work it out with you. I will work it out with you. Okay, we already have the probability notation. I mean the distribution notation. Now this helps us to summarize what we really need to see. Instead of keep on going back to this, right? Instead of keep on going back to this, we just refer to what we have there. Okay, now probability that 5 are vaccinated. So the number of students vaccinated is equals to 5. That's equals to binom what? CDF or PDF? PDF, probability density distribution function. Okay, not cumulative. Cumulative if you have at most. Now, if you have equal sign, then you use PDF. Okay, now right now you may not memorize it, but after some practice you will memorize it. But you need to keep on practicing though. Okay, do enough number of problems to put that in your, to memorize that. Then this will be 12, 0.25. Then I use my calculator. This is Binomial Pdf. Number of trials is 12. Probability of each success that person already vaccinated is 0.2. The X value, the number of successes we want, is 5. So 0.05315. 0.05315. To get exactly 3 people already vaccinated is around 5.3%. That's a low probability. Okay, but we are speaking about like only 1/5 of the whole student body. Not only this 12, 1/5 of the whole student body get vaccinated. So if you choose 12 of them, then the probability will be like this. Okay. Now, part B. What is the probability that the number of students vaccinated is 7? That's basically the same, right? Binom PDF 12, 0.27. Then when I use my calculator, binom PDF 12, 0.27, 0.00332. 0.00332. Yeah. Given that probability that a student has been vaccinated to be 20%, then the probability we get 7 of them vaccinated among these 12 is extremely low. It's extremely low. Okay, now how about part C? Probability that at most 6, so x is less than or equal to 6. That's probability of at most 6. That will be binom Cdf. Up to 6, at most 6, you use Cdf. Now that will be 12, 0.26. That's binom Cdf. Number of trials 12. Probability of each success 0.2. The x value is 6, up to 6 successes. 0.996096, so 0.99610. 0.99610. At most 6. Now, how about part D? What is the probability that 3, less than 3 are vaccinated? So probability that x is less than, no equal sign, less than 3. Let me do adjustment first. Less than 3 means up to what? It's up to 2, right? Because if you try to write it down, what 0, 1, 2, 3, and 4, and all the way to 12, when we say less than 3 means only up to 2. Okay, that's less than 3. Okay, so then the calculator notation by norm Cdf 12, 0.22. Okay, if you don't do this adjustment here, very likely you will put 3 there, which is wrong. When we say less than 3 for this type of distribution, it refers to only up to 2. That's why doing that adjustment will help you see better. Oh, you know what? When I punch my calculator, what should happen? Okay, so that will be binom Cdf 12, 0.2 up to 2. 0.558345, so 835. 0.55835. Part E. What is the probability that more than 7 are vaccinated? X is more than 7. More than 7. Let's visualize that first. 5, 6, 7, 8, all the way to 12. Now, when we say more than 7, does it include 7? More than 7, does it include 7? No, it's more than, right? It's more than 7 means starting from 8. Okay, it starts from 8. But we don't have calculator feature to compute from a certain number all the way up. No, what we have is from 0 up to a certain number. That's what we have. Okay, so that's equals to 1 minus probability that x is up to 7. Why is it up to 7, Thomas? Look at that box. I cannot think for you. I can explain to you, but I cannot think for you. Okay, you need to think for yourself. And if you think about it, if somebody else can think for you, then why do they need you? Okay, you want to make yourself to be significant. You want to make yourself to be needed in workforce later on. Then you need to do the thinking. In fact, you want to make money, you better be the one doing the thinking for other people. Okay, like when those of my former students can be tutors because what? Because they can think, and therefore they can help other students, my future students, to think, and they make a lot of money from there. Okay, you want to make money? That's how you do it. Okay, yeah. Tutoring recently is a very good field recently during this pandemic. Because a lot of students, then they cannot face their instructor directly, and some instructor actually get really busy with their health situation also, such that the students need more tutors, especially for those in high school. Yeah, especially for those in high schools. Then I get a lot of requests of tutoring. I myself not tutoring, but I get a lot of requests that I actually redirect to my students or my former students. You know, I usually teach Calculus 2, right? Okay, so I ask my Calculus 2 students, hey, you know what? Do you want to tutor this person? Do you want to tutor that person? Okay, I get this request. I get that request. And let my students make money. Okay, hey, that's $20, $25 per hour. That's easy money and tax-free, maybe. Depends on how do you want to report that to IRS, right? Okay, so let's see. So then I continue. Let me continue here. That will be 1 minus binom Cdf 12, 0.2 up to 7. That's 1 minus what? Binom Cdf, number of tries 12, probability of success 0.2 up to 7. 0.99942. 0.99942. But that's 1 minus though. So the probability that more than 7 already vaccinated is so small, 0.00058. Now, once we are done with probability, we will do something called inferential statistic. Now, inferential statistic is to decide if the number given to us already correct. Okay, so suppose they give you this fact. A survey, we randomly select 12 students. Probability that a student is vaccinated is 20%. However, when we actually select these 12 students, we found out that more than 7 of them already vaccinated. More than 7 of them already vaccinated. Okay, the probability for that to happen using these informations provided to us is very, very small. The probability that a student already vaccinated is 20%. But when we select 12 students, it turns out that more than 7 of them already vaccinated. Then there must be something different about these students. Maybe they are students in medical field. Maybe. Okay. Or it is possible that 0.2 given to us is already increased, not 0.2 anymore, but already much more. Or it is possible this student body happen to have access to the vaccination. Maybe most of these 12 students are actually the family member of a doctor, let's say. I'm not sure. In Indonesia, however, like if the doctor get vaccinated, then they will ask for exception for their families. Right? Can you vaccinate my children too at the same time? Okay. Why? Because I'm the doctor, right? I'm the doctor. You actually come to my facility. So why don't I give my children these vaccines first instead of those who actually need it more? You know, now in Indonesia, so most vaccines are actually free. But if you want to cut the line, like you want to get vaccinated without getting in line, then you pay. Okay, so what happened is some doctors can buy the vaccines and provide it to their quote unquote VIP. I call them VIP because they pay for something they're supposed to be able to get for free as long as they want to get in line. Okay, there's a good thing, bad thing about that though. I'm not trying to say bad things, it is bad. It's basically bribery. If you think about it, it is actually bribery. But then at the same time, you know, some people still don't want to get vaccinated in Indonesia, right? So even if you give them for free, they still say no. Okay, but by law, they cannot get vaccinated for free. Okay, so how about other people? They want to get vaccinated, but it's not their turn yet. So they pay for it. Okay, at least then the government can make some money to cover the cost of buying and distributing these vaccines, right? Okay, you want to cut the line? Fine, pay. Okay, but Thomas, a lot of people need it. Well, you can get it for free. Okay, just get in line. It's not, if it is not your turn yet, then wait. If it is already your turn, you can get it for free. But if it is already your turn, but you don't want to get it, then give it to somebody else, right? Okay, well, anyway, this is a case that we have, and we will have a lot of cases like this. One of a very well-known question that I encountered before is this. Instead of giving you that question, if you have a chance, take a look on my Winter 14. If you have a chance, Winter 14, quiz number 10. Now, that happens to be a real life question quiz. It's about textbook, okay? But you take a look yourself, okay? Now that question comes from binomial distribution. Now, instead of giving you that actual question, let me show you the practice done by a lot of airlines. For example, an airplane can seat, how to say that, can bring, let's make up a number, 70 passengers. Is this A, with A or E? I think it's with E. Maybe A, I don't know. So this airplane can bring 70 passengers, and probability that a passenger arrives at the airport for check-in before check-in is closed is, let's make it 90%. Okay, let's say you want to go to San Francisco by airplane, right? The probability that you arrive at the airport for check-in before they close the counter is 90%. So some people may not get there on time or may cancel. Okay, something happened that somebody some passenger cancels the trip. Okay, so the airline company sells actually 74 seats. See, there are only 70 seats available, right? But instead of only sell 70 seats, then the company actually sells 74 seats. Okay, now the question is find the probability of overbook. Find the probability of overbook. That is the number of passengers arrive before check-in is closed is more than the capacity. That is only 70 seats. So the airplane has 70 seats, but the company sells 74 instead. Now imagine if all 74 passengers, all 74 tickets purchased people show up, then they overbook, right? Then there must be 4 people cannot get up to the plane, right? They have to wait. Their flight need to be postponed. Okay, now then that's the case of overbook. But of course, there's a probability that not all 74 people show up on time. Okay, instead of selling exactly 70 seats, 70 tickets, and risking some people don't show up. Now imagine if your airline ticket is $100, right? And then you don't show up, what will happen? Do you need to buy another ticket, or they just put you in another flight? I mean, which one do you want? If you happen to be late, would you like them to tell you, oh, you know what? If you want a flight, you are really late. It's already, you cannot use that anymore, and you need to buy another ticket. Or do you prefer them to say, you know what? We will get you another flight. Which one you prefer? If you need to be late, right? Of course, you prefer not to have your ticket. You prefer don't need to buy another ticket, right? You prefer them to just like, hey, you know what? We get you to the next flight. Okay, but for that reason though, then they have sales 74 instead, or maybe more, or maybe slightly less. Why? Just in case that we get people like you come late, so the seat becomes empty, right? Instead of letting that be empty, give it to somebody who actually came before you, right? After all, we're gonna accommodate you anyway for the next flight if you come late. How about that? You see what I mean? Okay, now sometimes if it is really overbooked, then they will ask, is there any passenger willing to postpone their flight? And we will give them some cash back, let's say $50, $100 to make you happy to wait. Now, this is actually binomial distribution, which if you think about it, it's actually as the following. How many trials we have? So solution, let X be the number of passengers arrive before the check-in close. Now, this X will be binomially distributed. Why? There are 74 tickets sold. each of them may show up on time or not showing up on time, right? So there are 74 tickets sold. Okay, probability that they show up on time or before the check-in close is 90%. Now, so what is the probability? It's overbook. Now, it is overbooked if the number of people showing up is more than 70, right? You have only 70 seats available. Okay, then you have overbooked case, overbooked flight if the number of people arrive is more than the number of seats. Now we try to imagine it. Number of people arrive 0, 1, 2, all the way to 69, 70, 71, 72, 73, 74. At most 74. Why? Because only 74 tickets sold. Now, the case of overbook is when you have more than 70. Right? That's more than 70. And what is the probability that it is overbooked if the number of passengers arrive on time is more than 70? But we don't have that calculator feature. So let's take a look on the complement, which is up to 70. That's 1 minus probability that the number of passengers arriving on time is at most 70. Then the airline company has the right to refuse seating them. Hey, you come late. You know, we already closed the check-in counter. Now, what is that probability? That's 1 minus Binomial Cdf 74, 0.970. Okay. Now you want to keep the probability of overbook to be minimum, of course. But at the same time, if you don't want to have any overbook case, then just sell 70 seats. Then you never have a case of overbook. But you will have too many cases of empty seats. Okay. So there's a balance between you don't want to have overbooked too often, but at the same time, you don't want to have empty seats too often because that's actually a loss for the company, okay? Loss of income, right? If you don't like loss of income for yourself, then those companies do not like loss of income for themselves too, regardless how they will use that money, okay? Either it's for the stakeholder or for the employees, right? Okay, basically, they already provide the service regardless you show up or not. Okay, now the thing is, if you don't show up, you want them to accommodate them, then give it to somebody else. Okay, now then let's compute this. This is 1 minus. This is 1 minus, let's see, Binomial Pdf. Oh, Binomial Cdf, sorry. Binomial Cdf, the number of trials, 74, because there are 74 tickets sold. Probability somebody show up on time is 90%. And you want up to 70 only. The probability is 0.94594. 0.94594. So the probability that it is overbooked is 0.05406, approximately 5.4% probability, which is nearly unusual, right? So I guess 74 is a good number. Yeah, if you want to reduce this to be even less than 5%, then you make it you only sell 73 seats. But then you may have more case of empty seats. Okay, I hope this explains scientifically why some companies, some airline companies actually sells more tickets than the capacity they have. that explains why, for example, like when we open the classes, right, the number of seats supposed to be only 40, but when we open the class first time, we make it up to 45. Okay, we let the class take up to 45 students. Why? Because after 45 students on the first day of class, you may end up with only around 39 or 40 students. And let the teacher chooses if that teacher wants to take more students. Okay, and if you have a company, let's say a tour company, okay, we have, I think we have like 2 or 3 tour company in Monterey Park area. Okay, they have a bus that can cover 40 people. 40 people. But when they register, they may register up to 42 people or maybe even 44 people. Why? Because they know it is possible that some people actually cancel coming. You see what I mean? Okay, if they cancel coming, then the bus will be slightly emptier, right? Okay, if it is emptier, then the driver and the tour guide will get less tip money. You see? So this actually makes sense. In fact, if you want to put too many, if you want to sell more than, like, let's say 50 tickets for 40 seats bus, I think that's too much also, right? Okay, you don't want to overdo it, but not doing that, risking the company to lose some income, lose some money for not able to sell the seats that's supposed to be sold, but now empty, right? Okay. Now, again, our binomial distribution actually provides a framework and detailed work on how to compute the probability, and therefore it is up to the manager to decide, you know what, 5.4%, is it a chance that we want to take, sir or ma'am? Okay, like 5% of the time, like around 1 out of 20 trips, we will have some people complaining. Will that be okay for the manager? Okay. And if it is okay, is there any accommodation for those people who already come on time but cannot get to the plane? Okay. How to make them happy? Okay. And so on and so forth. Okay. The case that in winter 14, quiz number 10, if you take a look, that's about textbook. That's about textbook. It happens to be the day after I taught binomial distribution in my stats class at East LA College. And my department chair at West LA asked me those questions. Basically, the number of books we have available in the bookstore is only 350 textbook, Thomas. Okay, but we will have around 550 students taking that class in spring. So what happened is we have only 350 books, textbook available in the bookstore. I think that's the number. Maybe different. Okay, 350 textbook available in the bookstore. Okay, yet around 550 students are going to take that class in the spring. Now, of course, the number of textbook we have available is less than the number of students. So we have the risk of not having enough textbook to sell to students. Okay. Now the thing is, this department chair, Mr. Robertson, is someone very, very care of students. That's why he could not sleep because of that. And he asked me that question about textbook. I happen to be someone who worked very closely to a bookstore during that time. So he asked me, Thomas, do we need to worry about this? Do we need to order more from the publisher? And then I did the computation and the result is like, no, we have enough. we have enough. We have so enough that we can survive for another 1 year, even with only 350 textbook in the bookstore right now. And he was like so surprised. I say, I bet my finger. I bet my finger. I say, cut my finger, cut my pinky if I'm wrong. It's like, in other words, Thomas, his question was like, Thomas, you can just say that it's okay. We have enough with 350 books. But if our textbook is not enough, I will be the one the bookstore yelling at. I will be the one the students yelling at if the book's not enough. I say, don't worry. You get yelled, you can cut my finger. And I still have complete fingers until now. Okay, I even bet my fingers for 2 semesters instead of only that spring semester, spring 14. I use statistic. Okay, I say I don't really bet, I don't really gamble if I don't get anything in return, but I want to show Mr. Robertson my faith in what I learned in statistic. Okay, now if your statistic background is weak, if you don't know how to do this, then you will not be able to take that chance, and people can actually make fun of you. And in other words, they can make money from you. Okay, now let me go on further. The next thing are very theoretical and fast. Okay, let X be binomially distributed with NP, the number of trials is N, and probability of each success is P. Then the expected value of X, or the mean, is equals to N times P. Instead of using that probability distribution again, right? You can, if you want to do it very long way, but once it is a special distribution like this, binomial distribution, then the expected value is N times P. And the variance of this random variable, binomial random variable, is NPQ, where Q is probability of not successing. Okay, so if we use the example from above, let's say, for example, X is binomially distributed with 12, 0.2. Okay, then if you keep on selecting 12 students randomly, okay, then on average, the number of students already vaccinated will be 12 times 0.2, which is an average of 2.4. While the variance is 12 times 0.2 times 1 minus 0.2, that's 0.8. That is 1.92. Therefore, the standard deviation will be the square root of that. That's 1.38564. We get the mean, we get the standard deviation, then we can get the usual interval. Okay, the usual interval will be between maybe I do the lower bound, upper bound first. So lower fence, that's the mean, minus twice standard deviation. The upper fence is 2.4 plus 2 times standard deviation. We have done this in test 1. It will follow us many times. 2.4 minus 2 times 1.38564. That's negative 0.37128. For the plus 1, that's 5.17128. So the usual interval will be from negative something to 5 point something. So any outcomes outside of this usual interval will be outlier. So you don't expect to have 6 or more students already vaccinated. You don't expect that to happen. Okay, you expect around 2.4 more or less, maybe 2, maybe 3, maybe 1, okay, maybe 4, maybe even 5, right? But 6 is very unlikely already. Okay, that's the purpose for us to find the expected value and the variance. Now, again, next week, we will do problems regarding this, but let's take a look on our textbook and provide you the suggested homework from our textbook. Give me a second. Our textbook doesn't have a lot of problem. That's the thing. Not enough. Give me a second. Starting from number 13. No, I don't like it. 13 and 14, no. Starting from number 15. 15 up to number 29. To number 29. So suggested homework from this 5.2 is 15 to number 29. Let me see if we can do more. Number 37 is good. Number 39 is good. 37 and 39. Okay, now that's the end of our 5.2. After the break, we will work on Poisson distribution. So let's take a break, a long break this time, up to we come back at 12:10, like 30 minutes from now. The last section for our test 2 is 5.3. That's on Poisson distribution. Now, this section tends to be on the easy side, at least because every time we need to use Poisson distribution, they will tell us explicitly. Okay, the problem will tell us explicitly if we need Poisson distribution. Not like binomial distribution. Usually they don't tell us. They just tell us like, okay, we have this case, then compute probability. Okay. Now, when we have Poisson distribution, they always let us know. Now, Poisson distribution is this Poisson distribution usually defined as is usually defined as the distribution of number of incidents. You can call that number of successes over continuous over on continuous domain. Okay, now let's look back into binomial distribution first. Binomial distribution, you look at number of incidents or number of successes on n trials, where the number of trials is fixed. Okay, now Poisson distribution is when you are computing the probability for number of incidents on an interval. Let's say in some hours or over the stretch of 3 miles, so on and so forth. Okay, on an interval. Now, if X is Poisson distributed, then the notation will be X Poisson distributed, and then I will use mu for the average. Mu for the average. Let's say, for example, the number of customers going into CVS store next to East LA College between, let's say, 11 a.m. to 1 p.m. is Poisson distributed. It's a French, so we read that as Poisson. Is Poisson distributed with mean, let's say, 1.2 per minute. So on average, during that time period, we have 1.2 customers going into CVS. Okay, then the notation will be X, let X be, oops. So let X be the number of customers going to CVS. Then X will be Poisson distributed with mean 1.2 per minute. Okay, that's the notation. That's the distribution notation. Now, if you are already good with binomial distribution, then Poisson distribution tends to be a lot easier, because it depends only on one number, actually, only on the mean. Now, so suppose then I ask, find the probability of, find the probability of part A, let's say 2 customers in the next 1 minute. Exactly 2 customers in the next 1 minute. So in the stretch of the next 1 minute, what is the probability that the number of customers going in is exactly 2? It is exactly 2 and it is Poisson. So it's Poisson Pdf. Just like binomial case, if you want exactly equal to only 2 customers, like 2 incidents, then you will use Poisson Pdf. And the numbers inside will be 1.2, that's the average per minute, comma 2. That's the average per minute. Okay, and you want 2 events. The number of successes is 2. Now, how to punch it to our calculator? We go to the same distribution, second distribution, and you scroll down until you see Poisson Pdf. That's right below Binomial Cdf. Poisson Pdf. Make sure it's PDF though, in this case, right? Poisson Pdf. Now then, what is the lambda, which is the mean? The lambda is 1.2. The x value is 2. Poisson Pdf. So we get 21686. That's 0.21686. That's it. That's it. Now, it is a lot easier for us right now because introducing the calculator notation and how to punch that already done when we learn binomial distribution. Okay, now let's go on. How about probability of getting, let's say, 4 customers in the next 1 minute? How about probability of at most 3 customers in the next 1 minute? And how about the probability of more than 2? Okay, let's do it. Probability to have exactly 4 customers in the next 1 minute is probability x equals to 4. That's the probability notation. And then calculator notation, Poisson Pdf. The average is 1.2 and you want exactly 4 successes, 4 customers. That will be Poisson, again, distribution. You go scroll down all the way to Poisson's Pdf, and then the average is 1.2, and the number of successes you want is 4. That's 0.02602. 0.02602. That's the probability to have exactly 4 customers going to CVS, knowing that on average it's 1.2 customers per minute. Now, Poisson distribution is being used by a lot of store managers, not only for CVS, okay, but for Ralph. And I actually believe that was used heavily around 3 years ago at Albertson. At Albertson, they have this rule that you will not wait in line for more than 2 minutes. Why? Because somebody there, they use this Poisson distribution to compute, and from there they know how many people should be trained to be cashiers, so that people are not waiting too long on the line. Okay, right now it's a lot shorter because they use machines. Okay, which actually that machines that they use self-checkout, that's actually because of the increase of minimum wage though. Okay, so the way these companies think is like, hey, you know what? Instead of dealing with these employees that just go on strike here and there to ask for higher pay, let me just hire or purchase the checkout machine. Okay, so they can work 24 hours if we want, right? So one checkout machine, 10 checkout machine may be supervised by only one person. At Ralph, I know they use 6 self-checkout machine supervised by one staff. Okay, so instead of paying 6 people with cashier ability to run the cashier machine at the cashier, they just need one person. Okay, now the one I saw at Walmart is actually really extreme. That's like only one person for 10 or even 12 machines. You know, for me, that's extreme. Okay, they try to save money, but they try to save too much. Like that, the customer service becomes nearly zero. Okay, at Ralph, I live nearby Ralph. At Ralph, I'm always happy going there. Not trying to market Ralph. It's the one next to my house, basically. Okay, but with one person supervise 6 self-checkout machine, it's still, in my opinion, is reasonable. Okay, and even if I have a choice of checkout with a real cashier or with self-checkout, I prefer to do self-checkout. I can do it faster myself. I can do it faster myself, especially because I know what I need to do. Okay, if you are new to the system, then you may need some help, but eventually it's something easy to use. Okay, oops, why do I close that? Now then, how about probability of at most 3 customers in the next 1 minute? 3 customers in the next 1 minute, probability X is at most 3, as you can expect, because it is at most 3, up to 3, then we will use Poisson Cdf. Okay, we'll use Poisson Cdf. The average for 1 minute is 1.2, and you want that to be up to 3. Now, the position for Poisson Cdf is very, very far below. Very, very far below. You can just scroll down. Yeah, you can scroll down all the way. Very, very far below here. Okay, such that you may consider going up instead. So let me show you. Okay, this is the distribution, right? I go up instead. When I go up, I start from the very bottom. Do you see that? Right? If I go down, I start from number 1. If I go up from that number 1, I start from the last one. Now, Poisson Cdf is the third from the bottom. So maybe it's better for you to just go backward instead. Okay, lambda is 1.2, which is the mean. The mean for 1 minute. Okay, and then up to 3 successes, that will be 0.96623. 0.96623. That's the probability of having at most 3 customers. How about the probability of having more than 2 customers in the next 1 minute? Probability of more than 2 customers in the next 2 minutes. Now, how do we compute this? The number of customers in the next 1 minute, maybe 1, maybe 2, maybe 3, maybe 4, maybe 5. Actually, it's unlimited. It goes to infinity. Of course, it is impossible to get infinite number of people coming through CVS in 1 minute. That's of course impossible. Okay, but the assumption under Poisson distribution is the probability is still there, but it's just super small. Now, when we say more than 2, it means it starts from 3 to infinity. Now, we don't have that on our calculator, just like the binomial distribution. So what we will do is we take a look on the complement. Okay, that will be 1 minus probability that the number of customers will be at most 2. Now, if we go on further, this will be 1 minus Poisson Cdf 1.2 up to 2. Let's see our calculator. Oops, hold on. That's Poisson Cdf. I go backward. 1.2 up to 2. 0.87949. 0.87949. Let me check. 879487, so 949, right? Then subtract 1 from that will be, subtract from 1 to be more precise, that will be 0.12051. Okay, now, but notice that this is the probability for what happened in the next 1 minute. What if I ask the question slightly differently? Suppose I give you only one illustration or at most 2. So for example, what is the probability to get, let's say, 4 customers in 3 minutes? Not 1 minute anymore, but now it's in 3 minutes. So what happened is you need to see what is the average for 3 minutes. The mean is 1.2 per minute, right? Then what will the average be in 3 minutes? Multiply by 3, right? Multiply by 3. So the notation will be probability that x equals to 4 in 3 minutes, not 1 minute anymore. And that will be Poisson Pdf, because it's exactly 4 customers. Instead of using 1.2, right now you use 3.6. Is it okay? Let's see. So suppose I want to use that Poisson Pdf. And the nice thing about this, you can just type 3 times 1.2. 3 times 1.2 for the mean. For the x value is 4. Okay, and then punch it. And you get 19122. So the probability is 0.19122, like that. Okay. The key is this though. Once the time interval no longer 1 minute, then you need to adjust that, the average, to the number of minutes you need. So for 1 minute is 1.2. Then for 3 minutes, you multiply by 3. Okay. So you don't use 1.2 minutes anymore. Okay, the average for 3 minutes will be different from the average for 1 minute, right? Okay, now that's the case. Now let's see problems from our textbook. Let's do this number 5 and let's do number 6 and 8. I don't know if I have done that in the past, but let's do number 6 and 8. Let me copy this first. This is problem from our textbook. Let me see what happened. I have some light on. And then number 6. Yeah, let's do this number 6 first. Let me see what happened. My light is on. So this is number 6. Give me a sec. Okay, let's say we have this question. So assume that Poisson distribution applies. Assume that the mean number of Atlantic hurricanes in the United States is 6.1 per year. So that's our mean. Okay. They use lambda also for the mean of Poisson distribution. Give me a second. Something not really right about this. Sorry, I get this distracted because my light keeps on showing up, like this one here, as if like somebody tried to contact me, but I don't see anything though. I don't see anything. I don't know why. I don't know why the light's on. Okay, well, anyway, so the mean, which our textbook and a lot of other textbook also use lambda, but I emphasize that's the mean. So 6.1 hurricanes per year. Okay, now notation. So let x be the number of hurricanes a year. Then x is Poisson distributed with 6.1 per year. Now, part A. What is the probability that in a year, so it's still 1 year, there will be no hurricanes? That will be probability that x equals to 0. That will be Poisson's Pdf. (6.10). Okay, Poisson Pdf 6.10. We get 0.00224. That's 0.00224. That's the probability. Now, part B is interesting. Part B, in 55-year period, how many years are expected to be no hurricanes? This is not about the number of hurricanes in 1 year anymore, okay, in 1 year, okay, but this is how many years are expected. So this is expected value of no hurricanes years. So I need to define a new random variable. Let y be the number of years, not number of hurricanes anymore, number of years. The number of years without hurricanes. Now then, y will be not Poisson distributed, it will be binomially distributed. Either they have hurricanes or not. Okay, in particular year, you have 55 years. The probability of not having a hurricane is 0.00224. Okay, now the expected value, the number of years without hurricanes in 55 years will be this number multiplied by 55. This number multiplied by 55. That's 0.12336. 0.12336. Okay, now the thing is, that's the expected value. So we don't even expect to have any year without hurricane. You see? Is it possible to have a year without hurricane? That's possible. Okay, the probability is small, actually very small. The probability is very, very small. Okay, it's like the probability of having at least one hurricane in a year is 99% something. Okay, so if the probability of having no hurricane in a year is so small, then look at your expected number of years without hurricanes. Not even one. Okay, part C. How does the result from part B compare to the recent period of 55 years in which there were no years without any hurricanes? Does Poisson distribution work well here? Now you see it works well. As far as we know, in the last actually more than 100 years, we always have hurricanes in America, Atlantic hurricanes. We always have one in any given year. You see? Okay, so Poisson distribution actually well predicting the situation here. So in a year, the number of hurricanes is predicted by Poisson distribution. The number of years without hurricanes will follow binomial distribution. Why? Because of 55 years, which is 55 trials, right? 55 trials. How many years without hurricanes we expect? So that year, either we have hurricanes or we don't have hurricanes at all. So it becomes binomial distribution. Let's see number 8. By the way, hurricanes, just like earthquake, follows Poisson distribution very, very closely. Now, every October, as I remember, every October, we have that great shakeout. I wonder if you heard that before. Like every October on specific day, the government will tell us, hey, you know what? Every year on this date, they decided on annual basis. On this date, at this time, we do the great shakeout. Basically, assume the earthquake happened at that time. What do you do? Okay, assume that we have earthquake at that time, then what do you do? Now let's continue. Number 8 with the same given condition. Number 8, the number of hurricanes, I copied it down, is Poisson distributed with average 6.1 per year. Now part A, Find the probability that in a year there will be 4 hurricanes. Probability that X equals to 4. Probability that X equals to 4. It's Poisson distributed. So this is Poisson Pdf 6.14. Okay, again, we use our calculator to compute Poisson Pdf 6.14. 0.12939. 0.12939. So approximately 13% chance we have exactly 4 hurricanes. Part B. In a 55-year period, how many years are expected to have 4 hurricanes? Let Y be the number of years, not the number of hurricanes anymore. This is the number of years with 4 hurricanes. So this is Y is binomially distributed. Either that year you have 4 hurricanes or other than 4 hurricanes. Either 4 or not 4. Okay, but the number of tries is 55. The probability of having 4 hurricanes in a year is 0.12939. Then what is the expected value of the expected number of years where we have expected number of years where we have 4 hurricanes? Oh, by the way, you know what? I want to clarify how I get these numbers. I didn't write it down. I believe I say that, but I didn't write it down. Okay, I get that from multiplying 55, the n, times the p, 0.00224. Okay, that's how I get that. So here, the expected value will be 55 times 0.12939. We expect to have times 55, that will be 7.11663. 7.11663. Okay, how does the result from part B compare to the recent period of 55 years in which 10 years had 4 hurricanes? Our prediction says there should be around 7. Okay, that's expected value though. Can be more, can be less. Okay, can be more, can be less. But is 10 reasonable? Does Poisson distribution works well here? Poisson distribution, using Poisson distribution, we get this number. Now that is being compounded by binomial distribution, we get this number. That's why they make that question, to which 10 has 4 hurricanes. Now, how do we know that 10 is still reasonable or not? How do we know 10 is reasonable or not? Let's compute from here. Let's compute the usual interval. Okay, according to our estimation, the expected number of years with 4 hurricanes is around 7. Okay, but is 10 something usual? And let's find the usual interval. So the mean is the expected value, the mean, we compute that earlier, is 7.11663. How about the variance? That's n times p times q, which is 1 minus p. That's the variance. And later on, we will need to get the standard deviation. Now, let's compute this first. 55 times 0.12939 times 0.87061, I get 6.19565. So the standard deviation will be the square root of that number. That is 2.4891061. Also, the usual interval will have lower fans, 7.11663 minus 2 times the standard deviation. What is that? I get 2.13841, and the upper fans will be the mean plus twice the standard deviation. I get 12 something, 12.09485. So the usual interval will be from 2.13 something, like slightly more than 2, up to 12 point something. So even up to 12 hurricanes in a year is actually quite usual. It is incorrect, assuming this number 6.1 is a true number. Suppose it is a true number. Okay, it is incorrect for any journalist to claim that having 10 hurricanes in a year is too much. Well, you know the average is 6.1, right? So when you get 10, I mean, of these 55 years, if you get 10 of them, it's too many. No, according to our usual interval, no. The Poisson distribution that we assumed earlier, right, will give us the consequence that in 55 years, you expect more than 2 up to 12 years with 4 hurricanes in there. Now, the fact you have 10, which is different from the expected value 7, it's still okay because what? Even though it is not the same to the expected value, it is still within the usual interval. Now, the thing is, our journalists recently, to be honest with you, our journalists recently have too much into, for example, climate change, such that they ignore the statistic behind it. And if they see this number, well, according to your expected value, supposed to be 7, but we end up with 10. And they just stop there and let the audience think. Now, for those audience who don't know these numbers, they will think 10 is way more than what we expect, which is 7, right? But if you know how to do your statistic, then you will realize actually, no, with 6.1 average per year, 6.1 hurricanes per year, then to have 10 years with 4 hurricanes is actually well within the usual interval. It's well within usual interval. Okay, nothing extraordinary there. It's okay. It's possible. Okay, now let's do one more problem. I guess I don't want to deal with hurricanes anymore. Let's deal with something else. Would you like to choose something from here? Let's see number 14. Let's see number 14. Neuroblastoma is a rare form of cancer, occurs in 11 children in a million. Now, 4 cases of neuroblastoma occurred in Oak Park, Illinois, which had 12,429. Oh, let's see, what's the question? No, they don't have any question. They just give us that fact. Oh, I'm sorry. I copied that partially. We have ABCD. ABCD. So part A, assuming that neuroblastoma occurs as usual, like according to that probability, find the mean number of cases in groups of 12, 4 to 9. How many cases we expected? Well, okay, that's the P is actually 11 of 1 million. That's 0.000011. So either you have it or you don't have it, right? Now, assuming that you have 12,429 children, what is the mean supposed to be? Now, either that kid or that child, this is about children, right? Okay, the number of child is either that child has neuroblastoma or not. So let X be the number of children with neuroblastoma. It will be binomial distributed. Okay, 12, 4 to 9 with probability 0.000011. Okay, now the expected value will be 12,429 times 0.000011. 12429 times 0.000011. I get the expected value is supposed to be 0.13672. Now, using the rounded mean from part A, unrounded mean from part A, find the probability that the number of neuroblastoma cases in group of this is 0 or 1. The probability that the number of cases there is 0 or 1. Now, I will use binomial distribution to do this. Probability that X equals to 0 or 1. That's basically probability of X at most 1. Is it right? The probability that we have at most 1 case of neuroblastoma among these 12,429 children. That will be Binomial Cdf. The number of trials, 12,429. The probability of having neuroblastoma is 0.000011 up to 1. You know what? Let me move that instead. I don't like to go too far to the left. Let me move it down here. Okay, and we will use calculator to complete this. Binomial Pdf. 12429, comma 0.000011, comma 1. Oh, I'm sorry, should be binomial CDF. I use my hand calculator. Let me just use this calculator. Binomial CDF. Okay, so 12429. Enter. The probability is 0.000011 up to 1. The probability is 99146. The probability to have at most one such incident. So part C, what is the probability? So part C, what is the probability to have more than one case? More than one case, that is 1 minus probability that X is less than 1, less than equals to 1. Right? It's either 0, 1, 2, all the way to 12,429. Right? Okay, when we say more than 1, it refers to these cases. Now, we don't have a way to compute that, so we use the complement instead. Okay, which we already computed earlier. That's 1 minus 0.99146. That gives us 0.00854. The probability to have more than one cases of neuroblastoma will be very, very small. Very, very small. Then we can answer part D. Does the cluster of 4 cases appear to be attributable to random chance? Why or why not? If you happen to have that case, is it possible? That's possible. The probability is very, very small, however, such that we would easier to believe something else happened such that this number of incidents of 4 neuroblastomas in this community is attributable to something else than just to random chance. Maybe some genetic variation happens in that area, something to do with their water system or some radiation, maybe, we don't know. Okay, but we know that the probability is so small. Do you remember I talked about on the first day of class? So let me answer this. No, the answer is no, not to random chance. Why? It's very unlikely. Okay, it's already less than 5%. In fact, this is less than 1%. Okay, the incidence of having neuroblastoma in that area is much, much higher than supposed to be. But only 4 times, that's not a lot. Well, that's very a lot compared to what's supposed to be. Okay, not to random chance. There must be something else. Now, at the beginning of this semester, I mentioned about the probability that you need to do a makeup test to chance. And I say that you have good reason to need a makeup test in this one semester, happen to be the day that we have a test, is 3%. Right? Now, we have 4 tests and 1 final. So that's 5 trial, right? Okay. Now let X be the number of makeup tests needed. Okay, X is binomially distributed, 5 tests and 1 final. That's 5 trials or 5 tests we are talking about. The probability that you need a makeup test in 1 test is 0.3. What is the probability that somebody need at most 1 makeup test? of 5 tests. It's supposed to be only 4, test 1, test 2, test 3, and final, because I don't give makeup test for test 4. Okay, but let's do 5 right now. What is the probability at most 1? That will be Binomial Cdf 5, 0.031. That's the probability. .031. I use my handheld calculator. That's 0.99153. So the probability somebody needs more than 1 makeup test is 1 minus that number. Now, given this number, which is not too much different from that, right? Even slightly less than that. Okay. What is the probability that you really need more than 1 makeup test for some reason, for legitimate reason? It's so small. I'm sorry, it's so small such that you purposely set yourself up to avoid my tests on schedule. Now you see my reasoning why I don't give more than 1 quota? But Thomas, things happen. Yes, things happen to good and bad people, but in this case, at most once. Okay? More than that, something not right with you. And the thing is, I have one student yesterday send me an email, Thomas, can I do the makeup quizzes? I missed the last 2 quizzes. I say, no, you missed all the quizzes. And also the tests. Okay, and that person told me that, oh, you know what, that's because I'm sick, I get COVID. And then I look at the student access. I see that this person actually accessing the course, actually look at quiz 1 and look at quiz 2, 3, 4 in the past, many times, even downloaded them already. Okay, why this person then contact me now to ask for a makeup quiz? If you read my syllabus, I don't give makeup quiz for any reason. Right? But even if I want to, I don't have any reason. Why? You already print it out. You already download it. You don't submit it. Now you want to submit it after test 1. And it seems like this person don't even realize we have test last week. Okay. Now, if that person happened to listen to me right now, let me tell you, you have until tomorrow to make up your test 1. Okay. If tomorrow you don't take your test 1, I have to drop you. Okay. No, don't play with me. Don't play with me. I know my statistics so well. It is evidence-based. Okay, the evidence is you have not done those. Okay, and according to my numbers, right, the probability for that to happen is so small that you miss my quiz 0, which I can understand, maybe too early in the semester. Quiz 1, I cannot really understand because that's actually due on the end of the 3rd week of semester. Okay, quiz 2, 3, 4. Come on, man. Something not really right. Okay, the probability for you to miss quiz 0 pretty high. Quiz 1 is actually not high. Quiz 2, 3, 4 is actually very low. The probability you miss all 3, multiply all those. It says something about that person instead of my quiz. Now, you see how I argue using math, using statistic, how we catch people actually trying to, no, that person, I don't think that person is honest. I mean, I can tell that person is not honest. Okay, I even have a hard evidence, but even without those evidence, I have circumstantial evidence that given this, you miss all these quizzes, the probability for each one of them, probability that you miss all 3, it's so small already if it is up to random chance. It's so small already. Somebody just purposely not attending this class and now all of a sudden ask me to make accommodation for that person. No, I don't do that. Okay, what do you think? Do you want me to leave that person in class? You tell me. Thomas, something may happen to that person. Well, something happened to that person for 6 weeks. That person is supposed to drop the class, right? It's not that I don't want to give that person a chance. Well, why that person want to earn an F, right? And later on, when that person got an F, it will show up on my record as if I'm the one failed that student, right? Well, it's that student's fault. Okay, well, anyway, I want to come back to our lesson here. Okay, I'm basically done with 5.3. And if you want to do homework from there, oops, sorry, you can try from number 5 to number 5 to 15, I think. Number 5 to number 15. Number 5. So suggested homework for 5.3 is from number 5 to number 15. Okay, and next week, before we start working on problems from previous semesters, you can ask me these kind of questions. Okay, actually, I forgot to mention this. I supposed to mention this. Notice that this number 14 is actually on Poisson distribution section, right? This number 14. This is on Poisson distribution, Thomas, but the way you do it, you use binomial distribution. I use the proper, the precise way to do that, but we actually have estimation. We can use Poisson distribution to estimate binomial distribution. I believe that's what our textbook tried to say. Okay, here's the thing. Let me redo this problem, but this time I use Poisson distribution. Okay, they tell us that the P is 0.000011, right? Okay, and the number of people there is 12,429. So the average, the expected number of people having this is, according to binomial distribution, the expected is 0.13672 among 12,429 children. Okay, so part B, what is the probability that you have at most one? Now notice that I used binomial CDF earlier. We can use Poisson here. It's Poisson Cdf. Okay, 0.13672. That's the probability, right? The expected number of people children having neuroblastoma. Okay, now we approach this using Poisson distribution. Assume that mean is 0.13672. Now you want Poisson CDF up to 1. You use your calculator to compute that. I don't show you anymore. 0.13672, 1. We get 0.99146 also. Okay, so using Poisson CDF, that's the precise probability. Okay, that's the precise probability. Now, if we approximate using Poisson distribution, we are still quite accurate, even up to 5 decimal places. So if you have question, Thomas, why did you do that with binomial distribution? That's the supposed way to do it. However, the purpose of our textbook showing this method, showing this question in Poisson distribution section is because they try to show that we can approximate binomial distribution using Poisson distribution if it satisfies certain situation. What certain situation? The number of trials is way too big. If the number of trials is way too big, like how big is that? It's kind of hard to say. But we can say it's like, it's big enough, more than 3,000, let's say. To be more precise, if the mu is less than 5, as I remember. I don't remember precisely the rules, but as I remember, it's 5. 5 is such a special number there. Let me check on our textbook. They must mention it somewhere. Oh, I think it's here. It says that if you want to use Poisson to approximate binomial, then the sample size should be, the number of tries is at least 100, and the number of successes is at least 10. And that's the case we have here. The number of trials is more than 100, right? It's more than 100. Maybe I use different color. More than 100. A lot more than 100. And the average is less than 10. It's much, much less than 10. Okay, so we can use Poisson distribution to estimate binomial distribution. Okay, now, so Thomas, if you ask this question in the test, which method you want us to use? Either one, I will be happy if you get the number. Okay, if you know you can use Poisson, that would be great. If you know how to use that you can use binomial, I'll be happy either way. Okay, but remember, you can only use Poisson distribution to estimate binomial if, according to our textbook, that the number of trials is at least 100 and the mean is less than 10. Okay, as I know, it's actually less than 5. Yeah, supposed to be less than 5. The mu supposed to be less than 5. Okay, we call that the random probability distribution of rare events. Okay, now I will stop here. See you then next week if you want to come. Like what I said earlier, for next week, we finished 5.3 and therefore we finished the material for test 2. Next week, supposed to be no class, but I will go on Zoom and work on previous tests. I plan to go over Spring 20 test 2 with you. And I post the tests already on our discussion board. The week after that, we have spring break. And then the week after that, once we meet again after spring break, that will be your test 2 already. Okay, so this coming week is the time we need to prepare for our tests. Okay, see you then next week if possible. Otherwise, that will be 2 weeks from now. No, 3 weeks from now. Bye-bye.